He will talk ab- he will talk about holomorphic integrable system associated to the generalized Bruhat cells. So let's give him a welcome. All
Thanks a
right.
lot for Thanks a lot for Jun's invitation and introduction. It's my pleasure to take part in this workshop, in particular organized by the postgraduate students. Today I will introduce my research work on the holomorphic integrable systems associated to the generalized Bruhat cells. It is an approach of based on the Lie theory and the boson geometry. And that is the outline of today's talk. And first, I will introduce a holomorphic integrable system associated to the generalized Bruhat cells. And then I will introduce the well-known Kogan-Zalovinsky systems and to understand this kind of integral system from the viewpoint of the symplectic carrying. And last, I will generalize the Kogan-Zalovinsky system and to define the generalized results on the so-called generalized double Bruhat cells. Actually, the key points of this talk is the symplectic carrying. First, let me uh, do a few do a review on the boson geometries. First, boson algebra, and today's talk is over C. It is a complex algebra, commutative complex algebra A, together with a skew symmetric map. So it is so-called the boson bracket, such that first it is a B bracket and satisfies the Leibniz rule. And for the boson structures in geometry, we mean that it is actually a bivector field on a manifold or a variety, such that the induced bracket of this bivector field, it is a boson bracket on the local holomorphic functions. And in today's talk, we will also consider the so-called the T-boson manifold. It means that there exists a complex torus acting on this manifold, such that this torus action preserves this boson structure pi. And it is a remark that a symplectic manifold, it is indeed a non-degenerate boson manifold. It means that the pi sharp, the map from the cotangent bundle to tangent bundle, it is a non-degenerate. And then I will introduce the concept of the symplectic leaves and the T leaves. And for boson manifold and the pi and for a given pi sharp, and actually based on these boson structures, we can define a vector field, so-called the Hamiltonian vector field by the boson bracket. And then we can also define equivalent class by this Hamiltonian vector field, and it means that symplectic leaf through any point P, it is the collection of the points which are connected by the integral curves of the Hamiltonian vector field. It is the so-called symplectic leaves. You can also understand the symplectic leaves as the distribution of the pi sharp, the distribution of the image of the pi sharp. It is these two definitions are equivalent. And the so-called T leaf, it is it is roughly the T orbit of symplectic leaves, which means that it's a disjoint union of the T orbit of each point on the symplectic leaves. And any boson manifold, actually it is the disjoint union of the symplectic leaves or the T leaves. And it is my definition of the it is the definition of the integrable systems in my talk today. It means that here M it is a two-dimensional non-degenerate holomorphic Poisson manifold. And here we have a collection of n different holomorphic functions such that, and first it is algebraic independent. It means that if you write the df1 to df, it is not equal to zero or a dense subset of the M. And the second, it is that the functions of fj and arbitrary fj and fk, it is equals to it is equals to zero. The bottom bracket is equals to zero. And the goal today is to construct a completely holomorphic integral system associated to the double Bruhat cells and the Bruhat cells. And then let us go to some basic concepts in the E theory of the complex semi-simple Lie groups. That is also the building blocks of today of the constructions today. Here we suppose that G it is a simply connected complex semi-simple Lie group. And B and B minus is a pair of Borel and the opposite Borel subgroups. T is the maximal torus, and the W it is a Weyl group. And there is a famous Bruhat decomposition. It says that any complex semi-simple Lie group G, it can be written as the disjoint union of the BUB. It means that it is actually just the disjoint union of the B orbits. It is called it is a description of the B orbits, which is called the Bruhat decompositions. And similarly, on the flag brackets G mod B, it is also we can also decompose as the disjoint union of the Bruhat cells. And each BU over B, we call it a Bruhat cell. And actually, this Bruhat cell, it is the Bruhat cell and its generalization, the so-called generalized Bruhat cell, is the building blocks of into this talk, because each Bruhat cell it is indeed a fine space, and the dimension is equal to the length of the Weyl group element U. And now we introduce the notion of the double Bruhat cells. For arbitrary two given Weyl group element U and V, we define that the GUV, which is the BUB intersection with the B minus, VB minus, is the so-called double Bruhat cell. And what is the structure of the GUV? It is actually isomorphic to actually it is a localization of the fine space, and the calculator is isomorphic to C with the fine space times some circle CC star, and indeed this the total space G can be also written as the disjoint union of the double Bruhat cell as well. And what is the reduced version of the Bruhat cell? It means that we consider there's the homogeneous space of G mod T, and the double Bruhat cell over T, it is called a reduced double Bruhat cell. And for the reduced Bruhat cell, it is isomorphic. It is indeed a fine space whose dimension is equals to length of U plus length of V. Here we'll introduce some coordinates on the Bruhat cells and the double Bruhat cells. And the building blocks, it's the Bruhat cells. Actually, it is indeed the CW in this slice. And here we know that the decomposition will give the concrete decomposition of the Bruhat cells and the double Bruhat cells. And actually, for each element in the BWB, it can be uniquely decomposed in this way. Which the C it is the C is in the submanifold CW, which is actually isomorphic to the Bruhat cell B. It is the BWB over B, and at the same time, it can be also written in another way. And similarly, for any element in the B minus WB minus, it can be also uniquely decomposed as the G equals to B minus C. Also, it is equals to D times D minus prime. And for any element in the double Bruhat cell, so it can be uniquely decomposed in this way as well. And from the decomposition, we can realize that the building blocks of the Bruhat cell and double Bruhat cell it is this CW and the B and B minus. But indeed, this B and B minus can be realized as Bruhat cells times torus as well. Now we'll go to the multi-flag varieties and the generalized Bruhat cells. For any positive integers, and we define twisted action in this way, and this action actually comes under the multi-flag varieties. It is the quotient space of the Gn by the twisted action of Bn. Actually, this twisted action comes from the study of the so-called Schubert varieties, because the Schubert varieties it is singular and its singularity resolution actually, and the singularity resolution actually it is we will use the Bose-Samuelson varieties. The Bose-Samuelson varieties, the construction of Bose-Samuelson varieties, in the construction of the Bose-Samuelson varieties, this kind of twisted action and pairs. So it is why this kind of the twisted actions involved. And even in the study of the modular space of the flat connections, it is this kind of twisted actions also appears. Although the multi-flag lattice, it is the construction of the multi-flag lattice is depend on the twisted reactions, but actually it is isomorphic to the n copies of the normal flag lattice G mod B through this way. And you just need to multiply the first I elements together, and we can get this isomorphism. Now we'll give the definition of the generalized Bruhat cell. The for the multi-flag varieties, it has also the disjoint union decompositions of, and it can be decomposed as of the n-copies of the BUIB and the quotient out by the twisted action of the Qn as well. So in this way, we call we we can define the so-called generalized Bruhat cells, and we will denote it as the OU. And indeed, the generalized Bruhat cells, it is also the affine space, and whose dimension is the summation of the length of the UI. Now we'll give the motivation of the generalized Bruhat cells and explain why we will generalize the Bruhat cell. And it is because even inside the Lie group G, and we can regards the generalized Bruhat cells as our building blocks. For example, each BUB it is isomorphic to the generalized Bruhat cell BUB times BW not B over B and cross T. It means that even it means that even the subvarieties of the Lie group G can be identified with the generalized Bruhat cell times torus. And for the double Bruhat cell we introduced just now, it can also identify as a open subset of the generalized Bruhat cell and across some torus T. And actually, these are open embeddings from the double Bruhat cells into the generalized Bruhat cell O V inverse U times T. And we also apply the same building blocks of the CW. We can get the following identification of the generalized Bruhat cell. It means that for each element of the OU, it can be written as the product of some CUI in this way. And now we just need to identify the CU with a affine space, and then we can give some coordinates on the Bruhat cells or the generalized Bruhat cells. And based on this fact that if the length of the U1, U2 times U2 equals to their summation, then CU1, U2 equals to CU1 times CU2. Based on this fact, we can give each Bruhat cells or the generalized Bruhat cells by the following parameterizations. In this way, it means that actually each CSI it can be written as an exponential map of the ZI times the positive root vector e alpha I and twisted by the simple reflections as alpha I. And if we multiply these building blocks together, so we can give the parameterizations of the Bruhat cells or the generalized Bruhat cells. And because for the integrable system, we need functions. So, and based on the building blocks of the Bose-Simpson coordinates, now we try to define some nice regular functions. It is so-called the generous manners. And the generous manners defined in this way. And actually, once we have our Gauss decompositions, B minus B, and for arbitrary the fundamental weight, we can define the principal manners in this way. It is the principal manner you just uh, it is just regular functions. You can whose restriction to USB is defined and by the it maps from the element G to the torus part T in, in this way. And now we can generalize the definition of the principal manners to generalized manners. And it is a regular functions defined by the twisted of two variable elements. And it means that if we apply uh, the principal manners and on the twisted element of G by W1 inverse and the W2, and it looks like the conjugation. And then we can also define the regular functions on G. But in here we should notice that it is well defined when this G is simply connected. That is why we should assume that this G it is simply connected. If we do not apply the general manners, we do not the condition may be not that strong. Maybe the connected uh, the connected it is enough. But if we want to apply the general manners, we should assume that this G is simply connected. Now we can get and now once we have these principal manners and the general manners, we can define a class of regular functions on the OU inverse U. Here, there's some symmetry on this generalized variable element, and you just observe this this word, you will easily find that it is have a kind of the symmetry from S1 to SAN, and then the second part is SAN to S1. And then we can define a class of the regular functions on OU inverse U. It is that you multiply the from the kth element to the middle, and and then from the middle from the element CAN plus 1 in the middle to the element C to AN plus 1 minus K. It is also, it means that we just take the middle the middle two M elements and multiply the building blocks together and apply the generalized apply the principal manners, and we get a class of the regular functions. Actually, this collection of the regular functions it is the integrable system, but we equipped nice Boson structures on the generalized Bruhat cells. Now we'll introduce the Boson structures we need. And first, we should fix opinions of the root system. And the standard boson structures, it is actually the summation of the element E minus alpha by E alpha, which is the skew symmetric part of the so-called standard quasi-triangular matrix in the study of the Young-Baxter equations. And the boson structure, it is actually the left invariant bivector field minus the right invariant bivector field. which makes the Lie group G into a boson manifold. It is also a boson Lie group. And actually, each double Bruhat cells GUV, it has the T orbit of the simplex leaves of the G. It means that's why we will introduce the notion of the T leaf. It's because and that's why it is interesting to study the T leaf. It is because it is to study the double Bruhat cell because double Bruhat cell it is T leaves of the standard boson Lie G. And now we will introduce the standard boson structures on the generalized Bruhat cells. First, on the multi-frag lattice, we have a well-defined boson structures, which is projections from the direct product boson structures, and take the quotient. We can take the twisted quotient. We can get a well-defined structure on the multi-frag lattice Fn. And for the generalized Bruhat cells, actually it is a boson submanifold of the multi-frag lattice. And in particular, it is an important fact that the open submanifold, which is the OU inverse UE, means that the multiplications of this building blocks element Ci, the multiplication of them lies in the open of the open and opposite Bruhat cell B minus B over B. It is this open submanifold or UE inverse UE. It is a symplectic leaf of the generalized Bruhat cell or U inverse UE. So now we have a symplectic manifold or symplectic varieties here. And this I actually is just the regular functions we introduced just now, which comes from both Simpson coordinates and the principal minors. And this I forms a completely homogeneous integrable systems on the OU inverse UE. Because actually because this OU inverse U, it is generic symplectic, means that it has an open symplectic leaf or the OU inverse UE. And it is we can also call it a holomorphic integral system because it's generic symplectic. It is the first mean theorem in this talk. And now we'll show you some concrete examples in the both Samson coordinates. Here we take the exceptional case G equals to GB, G equals to G2, and the boson bracket can be computed by the program. And we'll notice that we can get such a polynomial boson structures. And the integrable system can be also computed directly, and it is F1, F2, F3. Then it is in this way. It is six-dimensional Phi space, and it is three. It is an integrable system, and whose functions are given by F1, F2, and 3. They are also polynomial functions as well. They are as well. Now let us go to the second part which is called the Kogan-Zalewiski systems. The Kogan-Zalewiski systems, and it is actually integral systems on the on a class of the symplectic leaves of the standard boson Lie groups. And the first we'll introduce some complete constructions of the so-called Fomin-Zalewiski twisted maps. It is a map from the GUV from the double Bruhat cell GUV to another double Bruhat cell GU inverse V inverse, which is defined in this way, defined on the building blocks. If you compared with the map in the Kogan in the Fomin-Zalewiski twisted maps, you will find that actually they are not the form there and the formula they are not same, but indeed but indeed I think it is a more more simple form of the Fomin-Zalewiski twisted map. It is somehow it's more easily to understand based on the building blocks of the unique decompositions of element. And in the boson geometry, we can also prove that the Fomin-Zalewiski twisted map is anti-boson with respect to the standard boson structure. And now we'll introduce some functions on the double Bruhat cells and the reduced double Bruhat cells. And the Fomin-Zalewiski twisted manners, it is defined by some, first, just defined by the Fomin-Zalewiski twisted maps and generalized manners. And this map actually it is depends on the choice of the reduced word of the U. And similarly, we can define twisted manners on the reduced case as well. And now we'll introduce the symplectic leaves of the standard boson structures of the G actually, and here the symplectic leaves we will use is this SUV, and actually this there's standard the symplectic leaves here as well, defined in this way. And for other spec leaves, actually you can understand as a translation of some elements in the torus of this SUV. And this also affects that for the reduced case, the reduced double Bruhat cell GUU over T is a symplectic leaves of the G mod T as well. And now we just need to restrict the Fomin-Zalewiski twisted manners to their symplectic leaves, and we can and then we can the Kogan-Zalewiski prove that it forms a complex complete holomorphic integrable systems on the symplectic leaves. And similarly, and Zhanghua Lu and Yipeng Mi prove that, and actually this kind the class of the Fomin-Zalewiski twisted manners on the reduced double Bruhat cell, it is also forms a completely integrable system of this or on the reduced double Bruhat cell. And actually, the construction of the Kogan-Zelinsky integral system, it is very complicated, and because it depends on trivial apply uh, both this forming Zelinsky two-state maps and the generalized manner. So, but in this talk, if you do not quite understand the details in this field here, it is not a problem because we have a better viewpoint to understand it. And because here we can first we can use this identification to identify the double parcels with with the generalized Bruhat cells times t. And for the boson geometry interpretation, they are also more boson isomorphism as well. Not only for the general case, but also for the reduced case. Uh, now we have now we will show you some examples of for some examples for the boson structure, and it is the you will see that for G equals to SL 3 and in the both Samson coordinates, so Kogan-Zelinsky integral system, it is more easier to write it down. And it is some examples. It means that in the Boston coordinates, actually, each coordinate function can be written as the manners in the SL3 phi. And the double bar cells can be also written concretely by the by, by the by the by the inequations of the polynomials of the manners. And it is the examples. It is the boson bracket that can be also read very concretely. And the Kogan-Zelinsky system, it is actually in this form, and the symplectic leaves can be also written down very clearly. And the symplectic leaves can actually, you will find that it is indeed some a square equals to some functions. The functions y1 and y, what is y1 and y2? It is y1 and y2. It is just the equations which defines the open Zariski open subset of the alpha space. It means that because it is open, Zariski open, so we'll always find some E equations y1 and y2, and then we just apply the a square, the part from the torus. The x squared equals to y1, b squared equals to y2, and then we can easily figure out the symplectic leaves in the bottom coordinates. So the first tour we can simplify the complicated integral in the complicated Kogan-Zelinsky system. It is the so-called bottom coordinate. Because apply the bottom coordinates, we can write down the symplectic leaves, bottom bracket, and the functions more the function in the integrable system more easily. And the second important viewpoint is that we'll understand from the simplex covering. The so-called simplex covering, it is a boson map. It is also a symplectic map. Here, the sigma 1 and sigma 2, they are both the symplectic manifolds or the non-degenerate boson manifolds. And if it is also a carry map, we call it symplectic carry. And actually, if we want to simplify the Kogadovsky system, the viewpoint is that we can apply the simplex carryings to pullbacks and integrable systems on the sigma 2 to sigma 1. And it is another fact. It is another identification of the symplectic leaves of the standard one. And here the fact is that the symplectic leaves through the point, the variable element and the identity for a nice representative of the WIs. It can be given by in this way. It is also the t square equals to identity. If the representative of the variable element is nice, and we can make the equations be t square equals to identity. But the more important factor is that the projection of this symplectic leaves over the T leaves OW identity. It is a boson carrying because the base space it is not symplectic. But if we suppose that this W is equals to U inverse, sorry, it is yes, if this W is equals to U inverse U, then the projection of the symplectic sigma U inverse U over the OU U inverse UE, it is a symplectic carry. And it is the key theorem. Maybe it is the key point to understand the Kokolazhevsky later. In particular, the relation of the Kokolazhevsky system and the Lu-Mi system on the generalized Bruhat cell. Because here we can obtain a class of the symplectic carry map, and we can pull back the integrable systems on the base space OU inverse UE to this to sigma U inverse U. It is a key point because here we have a symplectic carry. Then once we have this symplectic carrying, everything becomes easier. Because we just need to take a single variable element W, and we can get a symplectic carry map. And actually, the Kogan-Zalevinsky integral system K is just the pullback of the integral system I through the symplectic carrying. Yeah, so now we can see that the Kogan-Zalevinsky integral system is just the pullbacks of the integral system on the generalized Bruhat cells. But if you observe this symplectic carry, you will find that actually we can generalize our result, because here we just use a simple variable element U, but here it is the generalized variable element U. So, from this phenomenon, we can claim that we can generalize our integrable system from the double Bruhat cell to a more general space. So if we call it a generalized double Bruhat cell, so the question is that what is the space, what is the so-called generalized Bruhat cell, and what is the standardable structure on the generalized Bruhat cells, and what are the forming the Levinsky twisting maps on the generalized Bruhat cell, and how can we apply the symplectic carry maps over the generalized double Bruhat cells to the generalized double Bruhat cell? It is a natural question. And later we'll introduce this part. And the first, it is the construction of the generalized double Bruhat cell. And first you have some twisted quotient by the n copies of G over the n-1 copies of B. And we also go define the f minus n tutor that we have the n, it is n copies of G twisted quotient by the n-1 copies of B minus B. What is the so-called generous double Bruhat cell? It means that if we take m copies of the twisted double Bruhat cells, it means that it means that if we suppose that the multiplications of this element equals from the Fn tutor equals to the multiplications of the elements in the F minus n tutor. If it satisfies these equations, it means that it is the intersection of the so-called B bot UB times B minus bot V B minus intersection with the GMN, then it is the so-called the generous double Bruhat cell associated to UV. When U and V, it is a single Weyl group element. It is just the generalized Bruhat cell. We can easily see this fact. And recently, there are some recent work on the generalized Bruhat cell, and Shenlin Hui and Wang Daping, and they studied the cluster structure on the on the double Bose-Simpson cells, and which generalized the Bernstein forming the Levinsky is in cluster structures on the double Bruhat cell. And recently, Jianhua Lu, Victor Morgan, and I also construct a class of the symplectic group points, and whose objects are the generalized Bruhat cells, and whose morphisms are also related to the generalized double Bruhat cells. And then I will also tell you what is the boson structure. And the boson structure, it is a kind of the mixed product boson structure. And it is the boson structure, it is defined in this way by the mixed product by of the one, it is the B times B action. That one is B minus times B action. It is the boson structure. And similarly, we'll introduce the generalized the Levinsky multiplication map, and for each element in the double Bruhat for the generalized double Bruhat cell, it can be uniquely written in this way as well. So, but here you'll notice that the uniqueness of the decomposition depends on the position of the non-trivial B and B minus 1, because you from this construction we'll see that this BI, this B, you can put this B anywhere. You can put this B at the end of the element. you can put this B as the last position. You can also put this B in the first the positions. So and actually it provides some symmetries for the expressions of this element. And then I will introduce the Forman generalized Forman Delavinsky twisted map. And it is also the generalization of the Forman Delavinsky twisted map. And it means that first you fix some positions for this BI that is noted by K and L. And then we write down the unique expressions of the you write down the unique expressions, and then you just multiply the elements, the building blocks of the before the K together, and times the building blocks from the first one to the to the L-1th element of the DI together, and you also should multiply some BL minus 1 minus you and apply these evolutions of the G, and it is generalized forming the Lewinsky multiplication maps, and it is a generalization of forming the twisted map. And thus we have this kind of the forming the maps, then we can continue to tell our stories about the generalized Kogan-Delavinsky systems on the
Sorry,
generalized
Dr.
double
Yu. Sorry,
parcel.
Dr. Yu. You have 2 minutes left.
Hmm?
You have 2 minutes left. Time. You have 2 minutes left.
Yeah, it is. I have 10 minutes. 10 minutes more.
2 minutes
2 minutes.
left.
Okay. So lastly, and we will. So this some also some Poisson geometry technique, and the lastly we will introduce the construction of the Fomin-Zalewski twisted maps. And the first is that the so-called the Fomin-Zalewski twisted manners. The construction is also similar with the Fomin-Zalewski. It is just generalized the formulas of the whiskey twisted manners. And it is we apply the generalized formula of the multiplications on the G and apply the generalized manners to get a class of the regular functions. And on the reduced case, we can also generalize. We can also obtain this kind of this kind of the regular functions here. And for the symplectic leaves, this can be also so described by the by inside the by the translation of the so-called SUV. And the fact that is that it is a completely integral systems on the symplectic leaves SUU, and it is a completely integral system on the GUU over T, and it is a more general case than the double parcel. But although it is much more complicated, the construction is much more complicated than the usual generalized double parcel. But the idea it is the same. It is both of the above integral system. They are the pullbacks of the integrable systems of the I on the reduced double parcel. And in other words, we just describe this kind of the generalized Kogan-Delavinsky integral system on the generalized double parcels comes from pullback of the integral system of this I on the generalized Bruhat cells. Is this some reference about this talk? Okay, thank you very much.
Okay. Thank you, Dr. Yu, for his wonderful talk. So, so everyone, is there any questions for Dr. Yu about his talk?